Hello and welcome. I'm Kamal Takodra, a technical marketing engineer in the HP Aruba Networking Switching Business Unit. And today in this 10.14 1000 release update, I'm going to talk to you about the feature VXLAN overlay known multicast replication. So let's get into it. So today we'll cover an overview of the feature. Then we'll go into some more details. We'll look at some use cases. And then we'll go into some configuration and details too. And then we'll finish off with a short demo. For 10.14 1000, we now support known overlay multicast replication in the fabric using multicast in the underlay. This will be a single fabric with an IPv4 underlay, and in the overlay we'll support IPv4 and IPv6 as well as L2 and L3 VNIs. In terms of VTEPs, we'll support VSX, VSF and standalone VTEPs. And just to be clear, what I mean by this in terms of traffic types, it's a defined known multicast that a customer has defined for their multicast traffic. And then we'll support IGMP MLD and PIM sparse mode in the overlay. So for the underlay, the multicast routing protocol will be PIM bidirectional. And this uses a shared tree, star, G, using to build the multicast topology. And in fact, the CX VTEP switches themselves become the sources and receivers, but you don't need to configure that essentially. Now, PIM bidirectional scales better than PIM sparse mode when we have a many-to-many highly distributed sources and receivers, which is typical. Here we'll have sources and receivers distributed in the fabric. So all platforms in the fabric must support PIM bidirectional as a minimum, and then all VTEPs that are doing replication must support the replication mode multicast. And no feature pack is required for this enhancement. The supported platforms for multicast replication in Access Leaf are as shown, and then for non-replication that support PIM bidirectional, where they will typically have a spine aggregation core in the network, the 6400, 8325, 8360, 9300 and 10K can be used. Now let's look at the underlay replication journey. In 10.13 or less than or equal to, for EVPN VXLAN, we had head-end ingress replication. This is the default mode of replication, and this was for bum traffic as well as known overlay multicast defined traffic by a customer. Then moving on to 10.14, we then introduced underlay replication, and that was for broadcast, unicast and multicast traffic, and we used PIM bidirectional for that in the underlay, and PIM bidirectional supported a static RP at that time. You can see these updates in our ABC channel covering this. In 10.14 1000, we now have introduced for underlay replication known overlay multicast or defined multicast traffic by the customer, as well as having dynamic and phantom RP that provide HA and also some load sharing of multicast groups. Now let's look at head-end ingress versus underlay multicast replication. And we'll do this by looking at this topology and then reviewing some of the salient points. First of all, looking at head-end ingress replication, which is the default operation. We have multicast configured in the overlay of this fabric. The multicast receivers in this fabric, the three on the right, send an IGMP join. The IGMP joins get sent to the spines, which then push these down to the multicast source. The multicast source then replicates for each of the requesting VTEPs. Once that traffic hits the spine, it is then replicated and pushed down to each of the VTEPs. So really here in the head end or ingress replication, we see that there's inefficiencies in that we have the multicast traffic from the source replicated equivalent to the number of requests, and effectively the traffic increase is proportional to the number of VTEPs, VNIs, and can increase in the fabric. And the overall causal effects here are either the increased bandwidth requirement at the spines here, there's an increased bandwidth requirement at the source VTEP, and also the source VTEP ASICs require replication entries, which have a finite capacity. Now let's go ahead and look at underlay multicast replication. We start off with having multicast in the overlay, but this time we enable pin bidirectional in the underlay. As before, the multicast receivers send a IGMP join in this case. The multicast receivers send an underlay join to the rendezvous points here in the spine. The overlay still sends the IGMP joins on the overlay at the same time. This acts as a trigger for the source VTEP, which sends a single underlay traffic packet to join the RP. The spines then replicate the underlay traffic to the multicast receivers who joined that specific stream. So we've now created efficiencies here from a source VTEP perspective. Causal effects are we've decreased the bandwidth at spines compared to the head end ingress replication along here. We have also decreased the bandwidth at the source VTEP compared to head end ingress replication, and also the source VTEP ASIC decreases the amount of replication entries and reduces the burden overall on the source VTEP. In terms of use case, this means we can transition our EVPN VXLAN, either a DC or a campus, into underlay replication mode, provides us some more deterministic control of BUM and known overlay multicast traffic now. So it's more efficient use of switch resources and overall a lesser burden on source VTEPs. We increase the scale and the link usage has improvements. So let's go over some configuration details in brief. A number of things to mention here is that the note here that only we're providing partial configs and not full configurations to give you a flavor, but essentially these will be the parts of a configuration you need to add or adjust. And also the architectures shown here are only for illustrative purposes and not necessarily the supported topologies and can vary. So the first thing, or step one, that we need to do is we need to have pin bidirectional operation in the underlay. It must be in the default VRF. Please note that pin bidirectional and other multicast routing cannot coexist in the same VRF. So if you're using underlay replication, then you will stick to pin bidirectional as your multicast routing protocol. Now 10.14.1000 supports static, dynamic and phantom RP for pin bidirectional as an RP. Now in this example we've depicted a phantom RP here in the configuration, but you can use candidate BSR and candidate RP, which is not shown in the configuration. Please look at the 10.14.1000 update for pin bidirectional to see how to configure that. So in this example, we've got a primary and a backup, effectively phantom RPs, with the /30 being the active phantom RP with the preferred mask or the longest mask, and the /29 as the backup or the high availability RP. and then the actual phantom RP address is 1.210, which is configured on the leaves and the spine in this case. The next step is to have EVPN VXLAN operational as well as overlay multicast in your single fabric. So what we're showing here is the configuration of EVPN VXLAN as well as IGMP in the overlay in this specific VRF green here. So step 1 or step 2 are interchangeable. You can have EVPN VXLAN operational first and then pin bidirectional in the underlay, or the other way around. It makes no real difference. Now at this stage we still have head-end ingress replication. Step 3 is to add multicast replication to relevant VTEPs under the VXLAN interface. So the new commands are highlighted in red. We have the replication mode underlay multicast pin bidirectional multicast router group range, and we also have the replication mode underlay multicast pin bidirectional multicast group range. In 10.14 we introduced the flood group range, which was for bum traffic. So let's go over the multicast group range first. So the multicast group range is used to map the overlay to the underlay addresses for IGMP, MLD, PIM and PIM6. Now CX defaults to 239.1.4.0/22. This address range can actually be changed to the customer's requirements, and this is typically if this address range is being used elsewhere or part of that range is being used elsewhere. Now CX auto maps the overlay address to the underlay address, and that is not user configurable, or any intervention can't be made there, and so the only thing that you can change is the actual address range. Now we have 1024 hardware entries available, and this maps really well to this address range. Now best practice is for the multicast group range not to be used in another part of the fabric, either in the underlay or the overlay, and hence we have the ability to change this if there was a conflict. Now let's go to the router group range here. Now the router group range is a special group address, and it's really used to identify PIM routers. So typically it would be in the use case where on the access VTEPs or a lot of the VTEPs you have only L2 or IGMP or MLD, and then somewhere else upstream you have a layer 3 PIM router, and therefore this is what's used, this address range, to identify the PIM routers when you've got layer 2 with layer 3 upstream PIM routers. And the address range that CX defaults to is 239.1.1.0/24. And again, this can be changed if there is a conflict anywhere in the underlay or overlay. Now CX auto maps VNIs to multicast addresses again for the router group range, and for simplicity it's very similar to how the 10.14 flood range operates. We have 256 hardware entries available, and of course best practice for this is the router group range must not be used in any other part of the fabric, underlay or overlay. Now we go on to a short demo. In this demo topology, we are going to review EVPN VXLAN head-end ingress replication versus underlay replication when using multicast traffic in the overlay. In this topology, we have 3 VTEPs. VTEP 1, 192.168.1.20 on the CX6300, VTEP 2 at 192.168.1.159 on the other CX6300, and VTEP 3 at 192.168.160 on the VSX cluster. Each VTEP has a layer 2 VNI 180 on VTEP 1, VTEP 2 and VTEP 3. We will use VNI 180 throughout this demo. VTEP 1 will be the source VTEP in all cases. We will be bridging layer 2 multicast in this demo, which is a typical use case. 4 multicast frames will be sent from a host on VTEP 1, and hosts on VTEP 2 and VTEP 3 will join multicast group 239.2.2.1. We will then compare ingress head end versus underlay replication for multicast traffic. Now let's get to the demo. Let's start the packet capture. So that's started. Let's go across to our packet generator and send the 4 multicast frames. Now let's go back to our packet trace. Four multicast frames generated 8 frames at the source VTEP for stretch VNIs. That's 4 multicast frames times 2 VTEPs, which equals 8. So replication is proportional to the number of VTEPs across that stretched VNI. Taking a closer look at the first frame, we can see that the source of that frame is 192.168.120 VTEP 1, and the destination is 192.168.1.159, which is VTEP 2. If we look a bit further down, we will see that this is related to VNI 180 as we expected. And we can see it's a multicast frame. And we can see the destination multicast group 239.2.2.1. Now let's take a closer look at the second frame. Again, it's sourced at 168.1.20, which is VTEP 1. And we can see the destination is 192.168.1.160, which is VTEP 3. So this is the replication, first 2 frames of the first source multicast send that we sent from the traffic generator. And again, we can see this is related to VNI 180, and we can see that it's the source host of VTEP 1 host, which is here, and we can see that the destination is the multicast group 239.2.2.1. For each multicast frame sent, this is repeated per VTEP. We can see that on the third frame, we can see it's a source of .20 to .159, so that's VTEP 1 to VTEP 2, and then the fourth frame is VTEP 1 to VTEP 3. The cycle is repeated per multicast frame. Source VTEP frame replication increases with the number of VTEPs across the stretch VNI for multicast frames too. Now let's change to underlay replication. We see the default scopes selected by CX for the underlay multicast range. Aruba CX auto maps addressing, and VNI 180 for layer 2 bridged multicasts, which we're going to demonstrate, is mapped to group 239.1.4.1. in the underlay for VNI 180. Now let's start the packet capture again. That's going. Let's go to our packet generator and let's send the 4 frames. Let's go back to the packet capture. Now we see that we've only produced 4 frames for each 4 multicasts we've sent. Let's have a look in a bit more detail. First thing we see, we have source of 192.168.1.20 to a destination which is a multicast address 239.1.4.1. So source 120, which is VTEP 1, and then the destination multicast address of 239.1.4.1, which was the auto generated and auto mapped address for the L2 VNI for bridged multicast. Back to the trace. And we can see this is related to VNI 180, and we can see that the packet is sourced from host ending 1082 with a destination which is the multicast group 239.2.2.1. That is the same for subsequent packets. Again, going to 239.1.4.1. This cycle is repeated per multicast frame, and frame replication is only sent once per source VTEP per VNI stretch. This method reduces the processing requirement on source VTEPs for multicast frames when we revert to underlay replication. And this helps reduce the burden on the source VTEP in these types of scenarios. I hope that was useful and informative for you, and thank you for watching.